Okay, guys, this video is going to be about intermolecular forces. Now, just as a heads up, this is another video from Unit 7, right, which is heat and phases. However, I decided to redo the Lesson 2 notes. So these Lesson 2 notes were posted online, I'm pretty sure. They were also given out different in class, and these are a little bit of an augmentation to the unit or the Lesson 2 notes in your Unit 7 packet. Man, I wish I could just delete those last 20 seconds. If you just have your packet, there is some overlap. You'll notice that some of them look the same. You could probably make some notes as is. But anyways, we're going to talk about intermolecular forces for the next 5-6 minutes. So it's helpful to remember a couple things about this word. One, what is a molecule? So a molecule is a group of atoms that are covalently bonded. So this is a molecule. All right, I've got some water molecules right here, right, with my red oxygen and my yellow hydrogens. So molecules are individual, sorry about that. Molecules are individual groups of atoms that are covalently bonded. Whenever you see the word molecule, you should think of covalent. So group of atoms, covalently bonded, okay, as opposed to salts, right, which are ionically bonded. Notice there's no ions here, so we know that's not true. So which of these formulas represents a molecule? Right, it's got multiple atoms here. Okay, let's talk about inter versus intra. So an interstate, like Interstate 81, can take me from Phoenix all the way to Tennessee. I can go between states. Okay, and that's what inter means. So inter means between. All right. What we talked about back in October when we talked about bonding was we talked about intramolecular forces, right? Intra. Good job there, Mr. Fitz. Let's try that again. Intra. Okay, and this means within. Okay, so within this hydrogen chloride molecule, there is a covalent bond, right, keeping the molecule together. Between these molecules, this is an intermolecular force. And one of the things I want you guys to notice is we're drawing lines for the bonds because they're supposed to be like semi-permanent. They're supposed to be like a book binding. And then we're drawing dotted lines to say, hey, there's something going on here, but it's not nearly as strong as the bond between hydrogen and chlorine. Okay, just to give you another example, I've got two water molecules here. There are intramolecular bonds keeping them together, but the molecules, as you can see, are attracted to one another. Those are intermolecular forces. All right, so that brings us to our essential question. Why are some molecules, some elements, different phases at different temperatures? Or another way to put that is, why do some elements and molecules have different melting and boiling points? Why is water a liquid at room temperature, but the carbon dioxide coming out of my mouth is a gas at room temperature? And the reason is because some molecules are stickier than others. Right now, that's not a technical term, obviously, but some molecules really, really want to stick together, and other molecules, they don't really want to stick together. And the stickier the molecule is, the more energy required to separate the two molecules. All right. So water, for instance, is a super sticky molecule for a molecule its size. And I have to put energy in to separate them. I have to pull them apart like magnets. All right, I'm overcoming their intermolecular forces. So this stickiness is caused by something called intermolecular forces. And these intermolecular forces are attractive forces that exist between the molecules. They are weaker than the bonds within the molecules, right? Which is what we said earlier. So everything we're talking about today is weaker than covalent bonds. Now remember, think about the phases of matter that we talked about in an earlier video, right? What's the difference between the phases of matter? So, and I'm sorry this got a little smudged here, but in a solid, the particles are super close together, right? When something melts, you're pulling those guys apart, right? And now they're not as evenly structured, right? The molecules have room to move, or the particles have room to move. And then what's happening when this becomes a gas? Well, you're just pulling them apart, really far apart, and they're becoming a gas, right? The particles are kind of all over the place, taking up the full size of the container. So we're pulling these molecules apart. All right. And we have to put energy into doing that. So again, as we go from boiling, where things are relatively close together, to a gas where things are relatively far apart, right? We're overcoming these attractive forces. Right? Now, the stickier these molecules are, right, the stronger their intermolecular forces, the greater the temperature that's going to be needed to pull them apart. So the stronger the intermolecular forces, the higher the melting and boiling points. Right? Again, water is super sticky for a molecule its size, and therefore you have to put a lot of energy in to pull it apart, to melt it, and to boil it. Molecules with a weaker intermolecular force have lower melting and boiling points. All right, so I want you to pause the video here and see if you can answer these three questions. And what I want you to pay attention to is, here's the boiling point of three substances commonly found in the air. Who's got the strongest intermolecular forces? Who's got the weakest intermolecular forces? All right, and then take a look at this bottom question. So take a pause for just 30 seconds, see if you can answer it. Okay, hopefully you guys gave it a try. Now, what did we just get done saying? We just got done saying that a higher temperature is needed for molecules with strong intermolecular forces. So water is going to be the strongest intermolecular force. Right? It's the most sticky. Why? Because a higher temperature is needed to pull the molecules apart. Higher temp to pull apart. Okay, I'm like Shakespeare. All right, nitrogen's got the lowest temperature. Now, just a friendly reminder, negative 196 is a lower temperature than negative 78. So this is going to have the weakest intermolecular forces. Okay, lower temps are needed to pull them apart. Okay? And the reason is because you don't need to put much energy to pull nitrogen apart. Nitrogen's a gas at room temperature. There's nothing really keeping them together. The nitrogen's not very sticky. Okay? And hopefully it makes sense that if we had a solid version of all three of these guys, the nitrogen would fly apart because it's not really sticky. So there's nothing really keeping it together. Okay. Intermolecular forces sounds like some sort of nerdy science thing, but there's actually a lot of real world applications. Um, Everybody's seen a picture of some sort of bug. I'm sure that's the technical name for this guy on water, right? Water is such a sticky molecule with that cohesion and adhesion that it's able to walk across the surface. Snowflakes get their six-sided symmetry because of intermolecular forces. We'll talk more about that in class later. And the DNA helix, if you guys remember, the DNA helix, the double helix, is in the center, is made up of A's and T's and G's and C's being connected, right? And those connections have to be unzipped when the DNA replicates itself. Well, what's keeping those base pairs together? What's keeping those base pairs together is hydrogen bonding. Okay, I believe for the most part, but it's intermolecular forces. You don't want an actual chemical bond there. Right? What you want is an intermolecular force that doesn't require a lot of energy to break. Okay, so lots of real world applications. All right. Now, something's got to be causing this stickiness. And what's causing this stickiness is polarity. Remember what polarity is. Polar means different. Polar molecules have an uneven distribution of electrons, right? Or even simpler than that, they have an uneven distribution of charge across the molecule. They're like magnets. And the south pole of one magnet is always attracted to the north pole of another magnet. Well, the same thing's true with polar and nonpolar molecules. Polar molecules have a positive half and a negative half, and that positive half is going to be attracted. It's going to feel an attraction for the negative half of another one because opposites attract. So there are strong intermolecular forces with polar molecules, and therefore more energy is required to pull them apart, requiring higher melting points and boiling points. Okay, and if I haven't been clear so far, polar molecules are super sticky. Okay, nonpolar molecules, there isn't really an impetus for them to stick together. There's no positive half and negative half. So there's weak attractive forces. There are attractive forces between these guys, but they're much weaker compared to polar molecules. So therefore, less energy is required to pull them apart. All right. So based on what we just said, and based on what we said earlier, here's those same three components of air. Which of the molecules listed here is the most polar? Which of the molecules here is the least polar? So go ahead and pause the video for a moment, see if you can figure it out, and then we'll go over it. Okay, so welcome back. Most polar, right? Most polar means most sticky. Okay, so the most polar molecules are the ones that are going to have the highest temperature. You're going to need a higher temperature to pull them apart. So obviously water, okay, and nitrogen. Now, let's do a little reminder of polar versus nonpolar molecules. Remember, what's the difference between them? The difference between polar and nonpolar molecules is that polar molecules have a definitive positive and negative half, whereas nonpolar molecules are like mirrors. There's a symmetry, right? There's either negative charge on both sides, or there's positive charge on both sides, or there's no charge on both sides. So as a quick reminder, here's water. I'm going to draw the oxygen here in the middle of these axes, and I'm going to have one hydrogen coming down here and another hydrogen coming down here. And of course, I'm not going to forget my non-bonding electrons. Now, if I look up the electronegativities, here's that word from bonding. If I look up the electronegativities, remember that hydrogen, I think, is like 2.6, and I think oxygen is about 3.5. So electronegativity is the ability to attract electrons. The higher electronegativity is going to be partially negative. The lower electronegativity is going to be partially positive. So I've got oxygen here, which is partially negative on both sides of these bonds, and I've got some hydrogens, which are partially positive. Now, is this molecule polar, right? Or can I divide this molecule up into two different ends? And the answer is yes, right? If you take a look at the hydrogens here, there's kind of a positive portion of this molecule that's all kind of grouped together in this quadrant. Right? This is kind of a positive end of the molecule, and there's kind of a negative end of the molecule. And one of the things that we didn't really talk that much about in bonding, and we should have talked more about, is one of the reasons and one of the tells for a polar molecule is these non-bonding pairs, these lone pairs, which are forcing these hydrogens closer together, causing it to be polar. But I can draw a line separating the positive and negative half of this molecule. So water is asymmetrical, right? And therefore it is polar. Its charge is asymmetrical, so therefore it's polar. All right, carbon dioxide, go a little faster here. Just a reminder that carbon dioxide is a carbon in the middle with two oxygens. That oxygen is going to be slightly electronegative compared to the oxygen, which is slightly electropositive. Is this a polar molecule? It's not a polar molecule. If you notice, we've got some negative on one side, and we've got some negative on the other side, right? Equally surrounding a positive in the middle, right? This is like a mirror. You could take this molecule and kind of fold it in on itself, right? Its charge is like a mirror, so it's symmetrical. So if carbon dioxide is symmetrical, that means it's non-polar, right? We talked about SNAP, and we talked about bonding. So whether a molecule is polar or not has to do with the shape and not just the bonds. All right, nitrogen. Nitrogen is going to be nonpolar because there's no difference across the bond. The electronegativities are the same. The difference in electronegativity is 0. So this is also going to be symmetrical and nonpolar. Now, guys, just a reminder, right? What are some clues that something's nonpolar? Well, there's two clues, right? One is that it's diatomic, right? And the other is that it contains carbon. So nonpolar molecules versus polar molecules. All right, so we're coming up on the end here. There are kind of 2.5 types of intermolecular forces. All right, there's dipole-dipole forces, and this is the major attraction between polar molecules. So hydrogen and iodine have a positive and negative half always. So hopefully it makes sense that the negative half of one molecule is going to be attracted to the positive half of another molecule, right? So this is the primary attractive force in polar molecules, which makes sense. It's got pole in the name. So polar molecules feel a dipole-dipole attraction. Now, the one type of intermolecular force you actually have to know for Regents chemistry is this thing called hydrogen bonding. This is, notice I wrote 1A here. This is a type of this. So all hydrogen bonds are dipole-dipole forces. And this is a special kind of dipole force that exists between molecules that contain hydrogen and either fluorine, oxygen, or nitrogen. And what's special about these three elements, right, is that they're the most electronegative elements on the table. So they make really, really polar bonds. One thing I tell students is hydrogen bonding is tons of fun. Right? That's how you're going to remember. What are some examples of molecules that have hydrogen bonding? Well, water has hydrogen bonding. And every time you're asked about an intermolecular force affecting water, and you'll be asked that a lot in this course, it's going to be hydrogen bonding. What else? Well, what do you get when you have H and F? You get hydrogen fluoride. What do you get when you have H and N? You get NH3. So in order to have hydrogen bonding between molecules, right, the molecules have to have hydrogen and either oxygen, fluorine, or nitrogen. Now, hydrogen bonding is not a great name because it's not really bonding, right? At least the sense that we're going to talk about in high school. A greater name would be hydrogen attractions. Okay. So while we've got ionic bonding and covalent bonding and metallic bonding, hydrogen bonding is not really a type of bonding. Okay. Now, on a test or on a quiz or on the Regents, you want to write the actual name of the concept. Okay, but it's a flawed name, and I just wanted to bring that to your attention. What's hydrogen bonding look like? Hydrogen bonding looks like my magnetic water guys here, right? I've got hydrogen that's relatively positive from one water molecule. It gets close to the oxygen end of another water molecule, and they are attracted to one another. So I've got hydrogen and oxygen and hydrogen. Oop. Ignore these guys. Okay, and I've got oxygen and hydrogen and hydrogen. And you want to think of these as one big unit. And these guys are attracted to one another because the partially positive hydrogen and the partially negative oxygen feel an attraction for each other, kind of like magnets. We know that opposites attract. So that's what hydrogen bonding looks like. Positive end of one water molecule versus the negative end of another water molecule. There's lots of real-world examples of this, right? I always think this is an interesting picture. This Olympic swimmer, right, kind of rising to the surface for a moment. There's this almost skin of water, right, over his head because water makes this kind of skin. Same thing if you've ever had to put water drops in science class on a penny, right? It's almost, this water's being kept together by this cohesion and adhesion. It almost creates a skin. So lots of real-world examples. All right. I'm going to be honest. You don't need to know anything about dispersion forces, but I'm going to bring them up anyways for 2 minutes. Okay. Dispersion forces are the weakest intermolecular force. They exist between nonpolar molecules. Right? Now, how do you have attractive forces between nonpolar molecules? Well, at room temperature, hydrogen molecules will probably have an electron on one side and an electron on the other side. But these electrons are currently always whizzing back and forth between the atoms in the bond. All right, and the net result is that they're kind of on both sides. If you were to slow this movement down, where they were spending more time on one side and then more time on another side, instantaneously, you could have both the electrons on one side, just for an instant. And when that happens, just for an instant, you're creating a partial positive and partial negative. And that partial positive and partial negative are going to have an attraction for one another. Now, for something like hydrogen or nitrogen, it has to get super, super cold in order for this slowing down of the electrons to take place and the attraction to take place for it to liquefy. Right, so if you remember, if you take a look at the periodic table, the melting point and the boiling point for hydrogen are are super, super cold. Who feels these forces? The C-containing elements and the diatomic elements, the guys who come in pairs, like nitrogen and oxygen. Okay, so wrapping up here, I'm going to go through 2 questions. I'm going to do practice question 2 and practice question 4, and you guys can answer the other ones. Practice question 2, which molecule has the weakest intermolecular forces? Well, it's the one with the lowest boiling point, okay, because you don't need a high temperature to pull those guys apart. So that guy's going to be the weakest. Which type of intermolecular force is causing water's abnormally high boiling point? Okay. Water contains hydrogen and either fluorine, oxygen, or nitrogen. Right? Water's H2O, and therefore it's hydrogen bonding. Whenever you're asked about the intermolecular force of water, it's always going to be hydrogen bonding. And in this course, whenever you're asked about intermolecular forces, period, to name one, it's always hydrogen bonding. Okay, can you guys skip to the very end? Hydrogen bonding is strongest between the molecules of what? Well, hydrogen bonding exists. Hydrogen bonding is tons of fun, and it exists between hydrogen and either fluorine, oxygen, or nitrogen. The only one of these molecules that has that right combination is water. Which of the following is not a type of bonding? Ionic bonding, covalent bonding, and metallic bonding are all types of bonding. We spent a whole unit on it. Hydrogen bonding is not. Hydrogen bonding is an intermolecular attractive force. Okay, so that's what we discussed today. Intermolecular forces, right? Why are some substances solids at room temperature and some are liquids and gases? It depends on the stickiness. This stickiness is called intermolecular forces, and it's the result of molecules having a positive end and a negative end and feeling an attraction for one another. If you guys have any questions, let me know.